Okay, when you're ready, then please share your screen.
Okay, I think this example is good.
Okay.
Can you see my screen?
Yeah.
Um, so we're finding the shortest path from one source node
Hmm.
uh, to all other nodes.
Hmm.
So here we are starting with 0, and in the beginning, this is the distance, I think.
Hmm.
So this is the source node, and in the beginning, all the distances will be infinity. All the distances to the other nodes will be infinity, and the source will be 0.
Okay.
The source vertex. Then we go to each vertex that's available from the source node,
Hmm.
like these two, and update the path length. So it's 4 for both these nodes.
Okay.
Um, then we wait the next node that has the shortest path.
Are we
The
visiting four
next
now?
vertex. Yeah, this vertex. I guess
Okay.
you could
What do we
visit
do?
this also because they're both same.
Okay. So what happens when we visit four? Like, what do we do next after visiting the next node?
Then we have to look at all the nodes reachable from it. So now from 4, uh, there are no new nodes reachable, I think. There's only
Yeah,
4.
there's only zero and
Yeah,
four,
yeah.
and we can
Um,
reach.
so the path here, this path will get, it won't need to get updated because it's 4 plus 2, which is 6, and it's larger than the one that we had before, so we don't need to update it.
You mean the distance from 0 to 4?
Yes,
Okay. But why are we checking the distance from 0 if we're visiting 4 then?
we have to check the distance from 0 for all the nodes
So
because we're
anytime we
finding the
visit,
distance from 0,
okay, so anytime
the
we
shortest
visit a node,
distance.
we will have to check the distance of the adjacent nodes from 0, right?
Yeah,
Visiting is just to ensure we fill all the nodes with their proper weight information.
yeah, and to find out all the possible paths.
Okay. So here we
Um,
don't update 4 because we can reach 4, this 4 by from 0 with weight is just 4. So there's no need to take 4 plus 2 here because 4 plus 2
yeah,
is greater than 4. Okay.
yeah. Then after that we go to this node,
Mm-hmm.
and then check 7, 10, and 5. Uh, their distances from 0 and update them.
The shortest ones.
Yes, we hadn't put
Okay.
anything before, so we just
Okay.
update them with the distance from 0.
Was it even required to visit these nodes? I mean, we could have calculated the distances by just looking at it and fill them.
From 0.
Yeah. What's the advantage of visiting these ones?
I guess to find out the distance with all possible paths.
Okay.
And then after that, we visit 7 and 5,
Did
and
anything get updated?
5 plus 3 is less than 10. So earlier it was 10, and uh, from here you can do 4 plus 1 plus 3. So you update that to 8.
Okay, go up once. Let me see what's the difference between the two. Maybe just zoom out the screen a little bit so we can see it together. Control minus minus. Yeah, let's see what's happening there. So when we on the first instance when we visited 4, we took the distance as okay 4 plus 6. Okay, so what we were actually calculating is that uh, what will be the distance if it traverses through visiting that particular node which is in currently in which is the current node basically, correct?
Yeah,
Current vertex. So because it's 4, if you have to reach to 10 through 4, then that's the shortest possible one, which is 4 plus 6, which is 10. But now when you're visiting uh, 5 for
5.
instance, so if you have to traverse through reach 8 through 4 and 5, then the shortest distance is um, 8, correct? That's the
Yeah.
difference. Okay, it's too confusing, but okay. And this time we didn't visit one node, we visited two nodes together.
No, we visited 5 first.
Why
Uh,
7
5.
colored then?
Maybe they skipped the step.
Hmm. Okay, that's it, right?
So here they found, oh, are they saying 7 plus 2 is less than 8? So from here it would be 7 plus 2 for the node,
Yeah,
but
that's why
that
they
is
picked the
graded,
one
so
at the
you don't.
bottom. You don't need to update it.
Yeah,
I think they chose 5 first. I think they made a mistake in coloring 7. They shouldn't have colored it. 7 should have been
yeah,
colored in the last step.
yeah,
Okay, so to sum it up, we basically find the shortest possible path to all the nodes from the source node, right?
yeah,
So we start from a node and we fill the shortest possible weights to the adjacent nodes. Then we traverse to the next adjacent node, and from there we fill the weights for the all possible adjacent nodes. In case if we have to reach to those nodes from the currently visited node, and we just repeat this process till the end. Anytime we find that the value of the weighted the node the weight in the node is uh, greater, we don't update it because we always have to keep the shortest ones. Fine,
yeah.
that's it. Let's stop it. So let's see how we can simplify the explanation. I'll write it in my own words so it's easy for us to understand. Start from the source node. Uh, First, set all. Okay, I think they have already explained. I'll just copy that from there. Choose a starting source node. Assign infinity path values to all other nodes. Start from the source node and update adjacent nodes with the minimum possible minimum weight from. Yeah, I should put a graph also. It's easier to understand. I should put it in a different page. Where is it? Which slide are we on? How do I check which slide am I on? Okay, so choose. Okay, choose a source node. Example 0, and assign infinite path values to all other nodes. Start from the source node and update the adjacent node with minimum weight distance from the source node. In this step, since correct me where I'm going wrong, okay? In this step, since they should have named it, like A, B. It's so hard to address them. The adjacent nodes are four weights apart from this node. So we update their values. Then next is it possible for you to like um, how do I name them? Like how do I take too much time actually to do that? Traverse to the next adjacent node 4 and in teal color and update the weight of all the next adjacent adjacent node values from 0 if it traverses traverse through currently if the value
We have to traverse to the next adjacent node with the minimum distance.
okay from where minimum distance from where
From the source, from
at one
from the
point we
zero.
could be here. Yeah, but then at one point we could be here. So how will it have a minimum distance?
The minimum, uh, the unvisited node that has the minimum distance.
Okay. So the next unvisited in the source node. Then update the weight of all next adjacent node values from zero source. Traverse through zero through the current division. Keeping if the shortest distance is less less during fine. Repeat this process. Okay, moving on. Now it's Kruskal's algorithm. What we're gonna do is we'll continue for another half an hour with this, and then we'll take a break, 15 minutes, and we'll come back at 5:45. So 5:30 to 5:45, we take a break. Okay. Kruskal's algorithm is used to find the minimum spanning tree for a connected weighted graph. The main target of the algorithm is to find the subset of the edges using which we can traverse every vertex of the graph. So minimum spanning tree for connected weighted graph. First, sort all the edges from low weight to high. Now take the edge with the lowest weight and add it to the spanning tree. If the edge to be added creates a cycle, then reject the edge. Continue to add the edges until we reach all the vertices and a minimum spanning tree is created. Time complexity of Kruskal's algorithm is O E log E or O B log B, where E is the number of edges and B is the number of vertices. Application are layout electrical wires, wiring among cities, lay used to lay down LAN connections. I think we should add the application also. Fine. Let's take an example. So this is the vertex. Sorry, this is the weighted graph. We first write down A, B, C, A, D, all of those things, and we put the weights below them, and then we sort them in ascending order. Then first we add the edge AB with the weight 1. So starting from this in this sequence, we keep plotting them. Anytime it's forming a cycle, we reject it. So then we put this one, we put this one. Okay, we keep putting that. And finally we reach this. The minimum cost becomes this value. Okay. Now we go to search algorithm. Linear search is the easiest one. Just basically going from one element to another and searching for that element till the end of the list. So sequential search algorithm starts at one end, goes through each element of a list until the desired element is found. Otherwise, the search continues till the end of the data set. So starts. Okay. Start from the leftmost element of the array and one by one compare x with each element of the array. If x matches with an element, return the index. If x does not match with any element, return -1. So this is the one. Just loop through till the end of the array. Just keep comparing it. If you find it, return that. Otherwise, return -1. Binary search with example. So binary search is an algorithm used in a sorted array. So the key advantage is that the array is sorted. So then it's easily able to do its search. So it does that by repeatedly dividing the search interval in half. The idea of binary search is to use the information that array is sorted and reduce the time complexity to O log n. Okay, so used in sorted array, repeatedly divides the search interval in half, reduce time complexity. Begin with the mid element of the whole array as a search key. If the value of the search key is equal to the item, return an index of the search key. If the value of the item is to be searched is less than the mid element, decrease the interval to the left half, otherwise right half. Repeatedly check from the second point until it is found or the interval is empty. Okay, so consider an array with numbers so and so. Let search key be 4. Uh, let search key equals 4 be the element to be searched. Search key 4 is less than the middle element, therefore consider the left. So reduce this array into left half and consider 3, 4, 5 for the next iteration. Again, we choose the mid element, in this case 4, because the search is found, match is found, so we return that element. We don't have to do further search, but if it was not found, we'll repeat the same process over and over again. If there are more elements, continue to divide similarly by n by 2, n by 4, and so on. Then sorting algorithms, we have insertion sort, bubble sort, quick sort, two-way merge sort, heap sort, and topological sort. Insertion sort, I think we did this a few days ago. This is like sorting uh, playing cards. So basically, like holding cards, all the unsorted ones in one hand and the sorted ones will be on the second hand. Initially, the second hand will not contain any cards. So we start placing one card at a time into the other hand, and so let's say we put the first card, and the second card will check if it's greater than or equal to. If it's greater than, the new card is greater than the existing one, then we'll place it on the right, otherwise on the left, and we keep repeating this process. Sometimes you have to insert between two cards as well. The same process is followed here also. So here there are two lists that are maintained, sorted and unsorted, and the same process is followed. So this is a naturally occurring sorting method exemplified by a card player arranging the cards dealt to him. He picks up the card as they are dealt and inserts them into required position. Thus, at every step, we insert an item into proper place in an already ordered list. To find the correct position, search the list till an item is just greater than the target is found. So when we have to insert, like in real world, if we have to insert an item in the sorted list, we traverse through the entire list until we reach an element which is just larger than the one that we need to insert. Then shift all the items from this point one down the list, like towards the left, towards the right. Insert the target in vacated slot. Repeat this process for all the elements in the list. The result is a sorted list. The four, here we are going to insert one. So we'll insert one here and shift all other items this side. Then we have to insert three. So we have to look for an item that is just larger than the one we want to insert. So item that is just larger than the one we want to insert is 4. So we insert that before and shift all the items on the right. Same thing, same process is repeated. Iterate from array I1 to array n over the array. Item. Compare the current element to the predecessor. If the key element is smaller than the predecessor, compared to the elements before, move the greater elements one position up to make space for the swapped elements. Insertion mark first element is sorted. For each unsorted element, extract the element for j less than last sorted index down to 0. Current element j greater than x, sorted element to the right by 1, loop and insert x, insertion sort. Bubble sort, I think you have to write bubble sort what it is before explaining it. Okay, in bubble sort, we repeatedly swap the adjacent elements if they're not in order. This algorithm is not suitable for large data sets. Its average and worst case time complexity is quite high. So begin, read the array and the length of the array, and loop through the second element to the last element. I equals 1 to n. Loop from the last element to the current element. For j equals n minus 1 to I, swap two adjacent elements if they're not in order. Array j minus 1 is the previous element with the current one. If it's greater than equal to, should this be equal to or should this be greater than? You don't need to swap if this is equal, right? Swap array j minus 1, and so we start from the second element to the last element. And in the internal loop, we start from the last to the first. Compare the adjacent elements. If they're not in order, we swap. Okay. Quicksort. This is the most widely used internal sorting algorithm. In its basic form, it was invented by Carr Hoare in 1960. Its popularity lies in the ease of implementation, moderate use of resources, and acceptable behavior variety of sorting cases. The basis of quicksort is the divide and conquer strategy. Divide the problem list to be sorted into sub-problems until the solved problem is found. I think let's remove this unnecessary stuff. It'll consume time. Quick sort, we use divide and conquer strategy. We break the problem into subparts. An array is divided into subarrays by selecting a pivot element. The element selected from the array while dividing the array, the pivot element should be positioned in such a way that the elements less than the pivot are kept on the left side and the elements greater than the pivot are on the right side of the pivot. Okay. The left and the right subarrays are also divided using the same approach. This process continues until each subarray contains a single element. At this point, elements are already sorted. Finally, elements are combined to form a sorted array. He explained it so easily. It's not that easy. Choose a pivot and move it to the end of the array. So pivot, move it to the end of the array. Okay. Then item from the left that is larger than the pivot. Item from the right that is smaller than the pivot. Okay. I think we'll watch the video. It's better. Stop the broadcast. The reason